Hello everybody, I'm Fang Liu from Peking University. Today I will present the paper A Self-Attentional Neural Architecture for Code Completion with Multitask Learning. First, I will give an overview of our paper. Code completion is one of the most useful features in IDEs that can accelerate software development by suggesting next token in real time. Recent studies have shown that statistical language models can improve the performance of code completion tools through learning from large-scale software repositories. However, these models suffer from three major drawbacks. The hierarchical structure information of programs is not fully utilized in the program's representation. The long-term dependency cannot be well captured by these language models. Existing approaches perform a specific task in one model, which lead to the underuse of the information from related tasks. To address these challenges, we propose a self-attentional neural architecture for code completion with multitask learning. To utilize hierarchical structure information of the programs, we consider the path from the predicting node to the root node. To capture the long-term dependency in programs, we adopt Transformer XL network as the base language model. To enable the knowledge sharing between related tasks, we propose a multitask learning framework to learn two related tasks in code completion jointly. Now let's look at a motivating example. This figure shows an AST of Python code snippet. When predicting the node break, the contextual sequence contains all the nodes in the tree except break if the tree is flattened in depth first traversal. The hierarchical level of the predicting node is ignored. Well, if the path from the predicting node to the root node is introduced into the program's representation explicitly, the structure level of the predicting node can be utilized. The model will probably realize that the predicting node is in the if statement that is nested in a while statement. For the model's learning mechanism, when the model is going to predict the node num0, the type of the node num conveys the message that the node's value is a number. The model will probably predict a number as the value of the node. Based on this analysis, we believe that the type and the value of the node should be predicted jointly. Now let's turn to the proposed model. This figure shows the architecture of our proposed model. We adopt Transformer XL-based language model as a partial AST encoder, and also design a path-to-root encoder to capture the hierarchical information of the predicting node. Then we combine the output of these two encoders together and use it to make predictions on the next node's type and value. During this process, multitask learning is adopted to learn these two tasks jointly. For programs representation, we use ASTs to represent programs. First, we flatten the AST in order traversal to produce a sequence of nodes. Then we represent both the type and the value as vectors and concatenate them as the final representation of the node. For partial AST encoder, we adopt the Transformer XL network to encode the partial AST. In this figure, S-tau and S-tau plus 1 represent two consecutive code segments. The nth layer hidden state for the segment S-tau plus 1 is computed as this formula. Compared to the standard transformer architecture, the crucial difference lies in that the key and the value in the network are conditioned on the previous segment, so that the network can reuse the previous segment as actual context and capture long-term dependency. For the path-to-root encoder, we design a bidirectional LSTM-based network to encode the path from the predicting node to the root node. Here I'm representing the length of the path. For each time step, the hidden states for both directions of the bi-LSTM are computed as this formula. And finally, we concatenate the final hidden state of the both directions to obtain the final path vector P. We adopt the task-specific output layers to produce the output. Here we perform two tasks in our model, that is, predict the next node's type and predict next node's value. The output of the partial AST encoder H and the path vector P are concatenated to compute the task-specific output vector O. Then we use softmax function to produce the probability distribution of the output Y. To learn the related tasks jointly, we adopt a weighted sum over the task-specific losses as the final loss. By default, we set the weights for the two tasks as 0.5 and 0.5 respectively. Now let's look at the experiment and analysis. For the datasets, we use three programming languages: Python, Java, and JavaScript. All the datasets are from previous research. Each dataset contains 100,000 training programs and 50,000 test programs. For all the datasets, each program is represented in serialized AST node sequence format. This table shows detailed information of the datasets. For metrics, we use top 1 accuracy to evaluate the model's performance. Besides, to measure the room for improvement, we also adopt normalized improvement in accuracy as another metric. Here are some parameter settings of our model. During the training process, we adopt cross-entropy as loss function and Adam optimizer. Each experiment is run for 3 times and the average result is reported. Now let's see the research questions and results. The first research question is: how does our proposed approach perform in code completion when compared with state-of-the-art models? We compare our model with 2 state-of-the-art baselines. The first is an n-gram-based model, and the second is a pointer network-based model. This table shows the results. As can be seen from the results, on all the 3 datasets, our model outperforms all the baselines on both the type and value prediction tasks. And the second research question is: what is the effectiveness of each component for our proposed model? To answer this research question, we conduct experiments without either multitask learning or path-to-root encoder. And we also present the results on vanilla transformer XL network by removing both of these 2 components. Besides, to verify whether capturing the long-term dependency from the input programs helps, we give the results of removing the recurrent mechanism from our full model. As seen from the results, removing either multitask learning or the path-to-root encoder results in a drop in accuracy, and removing multitask learning drops more, which demonstrates that both the multitask learning and path-to-root encoder are necessary to improve the performance, and multitask learning contributes more to the improvements. When removing the recurrent mechanism from our full model, the accuracy drops a lot, even lower than the vanilla transformer XL network. This demonstrates that capturing long-range dependency is of great importance and necessity for language modeling, and it serves as the basis of other improvements. To evaluate the cost of the improvements, we count the number of parameters and record the training time of our model and baseline models. To evaluate the cost of our proposed components, we also present the data of removing each of the components from our model. Compared to pointer mixture network, our model uses 59% of the parameter budget and spends 74% of the runtime to train, and can still outperform them. Compared with vanilla transformer XL, we apply multitask learning to learn 2 tasks jointly and also add a new path-to-root encoder in it, which will lead to an increase of the trainable parameters and training time. However, the increase is slight and acceptable. In our multitask learning-based model, we use a weighted sum over task-specific losses as the final loss. The performance of the model is related to the choice of the weighting between the tasks' loss. To show the effect of the weights, we present the results of different weight settings on our model. In this table, alpha 1 is the weight of the loss for the next node's type prediction task, and alpha 2 is the weight for the next node's value prediction task. When one of the weights is set to 0, the model becomes a single task model. As seen from the results, when giving more weight to a task's loss, the accuracy of this task will be increased, However, when assigning a high weight to one task, the advantage of the multitask learning would be affected, which results in a poor performance. Predicting the structure of the code, such as loops, if statement, and exception handling statement, is overall a very hard task. Rachel et al. Define a set of types on JavaScript that are hard to predict and name them as difficult type prediction. We evaluate our model's performance on this type's prediction and compare our model with pointer mixture network on the same test set. As seen from the results, our model outperforms pointer mixture network by a large margin in all of these types. This demonstrates that our model can discover structure of the programs and achieve an excellent generalization performance on structure predictions. Here we present a code completion examples on Python to analyze the performance of our proposed model and mainly analyze the effect of the path information and the multitask learning. We take several positions in a Python code snippet to test the performance of our model and the baseline model. In the first example, the target prediction name is a parameter for the function init, and its corresponding node type is non-param. The path implies that the prediction is a parameter of a function. Thus, it can help our model to make the correct prediction on the node's type. While for the baseline model, it can only learn from sequential context and fail to produce the right prediction. Similarly, in the third example, the target prediction diff means a function definition, where its corresponding node type is function diff. With the information contained in the path, our model can make the correct prediction while the baseline model fails. In the second example, the target prediction self is not a new variable and has been used in a previous context. By correctly predicting name load in the node type prediction task, our model can realize the value of the node is an already used value in the previous context. Thus, it can identify the value from context through a pointer mechanism. For the baseline model, it may not realize the prediction is a variable accessing operation without the help of the related task. Thus, it just predicts empty, which is the most frequent node value in our corpus. Finally, I would like to make a conclusion and discuss potential future research directions. We propose a multitask learning-based self-attentional neural architecture for code completion. For code representation, we propose a novel method to model the hierarchical information of the predicting node explicitly. And to capture the long-term dependency in the programs, we apply the Transformer XL network as the base language model. And we also apply multitask learning to enable the knowledge sharing between related tasks. In the future, we plan to improve the effectiveness of our proposed model by the following approaches. First, we plan to introduce domain-specific constraints such as grammar rules, static type information. And we also plan to build a token-level multitask model. And finally, we want to try pre-trained language model to learn contextualized embedding for the source code. Thank you very much for your kind attention.